Good morning, everyone. Welcome to the EasyPower Tuesday Refresher. My name is Jim Chastain. I'm an apps engineer here at EasyPower, and I'd like to welcome all to the discussion. Recently, an EasyPower tool owner contacted us with several questions about his first arc flash project involving mostly voltages below 240 volts. Today, I want to convey the essence of the conversation because it's a topic that seems to come up more and more frequently as owners of small to medium-sized companies grow to understand their obligation to employee safety in terms of arc flash assessment and prevention. And as we are inclined to do, we'd like to start this particular installation with our poll question. If you would please, this will be real quick, but if you would please provide some feedback. In the first case, it's how often do your projects include 240 volt? And here's how people weighed in on that particular topic. And as you would expect, it's just happening more and more often. And then the second question is how often do you actually see the need to label single phase distribution systems? And here's how people voted on that one. As a point of order, for those of you that are new to EasyPower, all EasyPower users with current maintenance status have virtually unlimited access to tech support via email and phone. And when you contact EasyPower Tech Support, you're talking to a degreed engineer, and they are all located in sunny downtown Tualatin, Oregon. Now, when a new customer purchases the tools, we offer a no-cost 1-hour tool orientation online. We call this session a PowerStart, and the primary goal is to help new users get up and running on their first project. Usually they will send me their first stab at doing a one-line drawing, and then we spend the time to take that initial attempt to the point of actually generating arc flash results. This usually includes some fairly significant discussions about the basics of the system modeling and arc flash calculations. Frequently, these first projects involve lower voltage and lower energy subsystems. And so this, what I'll be doing here as we walk through this is relaying some of the, significant questions that came up. And the first question was, okay, I've done my one line. I'm looking at incident energy, and it seems pretty high. What do I do about this? Well, before you get to this point, what I'd like to suggest is you really want to size up the big picture of your whole system and start with a very simple one-line diagram, literally one line from your utility or energy source to the lowest load that you need to label, and include in that one line or that elevation or schematic one each of the elements that are in the system that need to be labeled. So transformers, switch gears, relays, motors, and the like. Now, I don't mean to imply by that you need a label on the transformers. It's just a key element in my calculation, so it needs to be part of the one line. And the advantage of this is it allows you to walk through the mechanics of the tools and basically adopt your own process for checking for errors, first in the data collection and modeling, and then second in the analysis side of it. So this is essentially my process that I use and the way I proceed with these types of conversations. So as you would expect, utility data is fairly significant and frequently one of the most difficult areas to get correct data on. Before I forget, in the handout section of the control box for this webinar, I've included 3 handouts, one of which is a practical solution guide to arc flash calculations, and in it is a discussion on how to work with utility companies and how to make some estimates if for some reason you can't get the data that you need from the utility company. back to my process for errors. So the utility data is important. Transformer nameplate data is very important, probably highest on the list, is because the transformer acts as the energy buffer between our system and the rest of the world. And then you'll see as we get into the details on this particular project, it's very helpful to utilize a facility or a utility in the tools called Database Browser to compare the data entry. And then again, this is part of the very simplistic one line. And as you are able to get a sense for what elements you need to include in your study, it gives you the ability to go out and do a better job of data collection at the same time. And then as a result of completing their one-line diagram and our discussion, you'll be able to kind of get into the nuances of arc flash. Now, there's really not a prescribed certification as a prerequisite for performing arc flash studies, but there is a requirement that people doing arc flash studies have experience in studies of similar systems. This process that I'm going through, and that is having an initial discussion and then accessing experts in tech support when you have specific questions, is a way to expand that experience for people new to the studies. All right, so these are the primary steps or the primary areas I'm going to be talking about here shortly. Okay, so the statement was, well, they gave us the fault current for the secondary side of the transformer. What do I do with that? Well, it's fine if that's the way that data was presented to you by the utility company, but you need to make sure that that you model it correctly. And kind of a note to self, one way to deal with that is to not include the transformer, but to just model or modify, customize the utility icon as your energy source. And so you'll see as we get into this drawing, that's essentially what the customer did. But if you take a closer look, you may be taken back with the elements or the units that he was using in his one line. So let me jump into the tool. This is the file that was sent. And if we zoom into the utility icon and open up, one more thing, I'm in EasySolve, which is utilized in a lot of cases where you have a modest to simple system and no need for coordination. So EasySolve makes a nice solution for those types of applications. And so what we've done is we've taken the utility data icon and modified it with the information that the utility company gave us at the output of the transformer. So in this case, the voltage was 208 volts. The unit is kiloamps, but as you can see, with the numbers that he entered, more than likely he missed a decimal point, and that the utility company probably gave him amps, and the tool is asking for kiloamps. So that one issue alone, if we kind of leave this as it is and go back to his initial question was, okay, my incident energy seems kind of high. That issue alone might cause us problems. And interestingly enough, he does have here 12 calories on some of his remote panels. Now, looking at it this way kind of reinforces the point I'm trying to make, which is rather than jump to the calculation results as my debug criteria, be a little bit more careful in doing a very simplified one-line diagram so you don't have a lot of clutter that gets in the way. So back to where we want to change the decimal point. And the other thing that's a little strange about the data, and I advise that you may want to double check, most of the time the single line to ground short circuit is less than the three-phase. Three-phase is usually higher, worst case current. So that's another word to the wise. So we're going to leave it as it is. and assume that this is correct. Okay, so again, what we want to do is make sure we enter the data correctly, and especially in the early stages, use a little bit of a jaundiced eye at looking at the units involved when we're doing data entry. All voltages in EasyPower in kilovolts, and you'll see you can actually adjust this. Let me go back to the tool. As we get into short circuit, we have the ability, if you right click in an open area and go to short circuit options, my units are going to be in kiloamps no matter what I do. So just be careful that you're entering the data appropriately. All right, so back to where we were. Now, one more note about missing data, and that is when I asked if the bus ratings were all provided or input, the response was the client did not provide that information. Therein lies a little bit of an issue in being able to provide an accurate analysis. And I may spend too long on this, but let me go ahead and go through it. The lack of the data will prevent the equipment duty function of the tool from operating properly, and in some ways it's kind of a false sense of security because you're not seeing any errors. And if you get right down to it, the whole reason, well, I shouldn't say the whole reason, the primary step and the reason for the first step in an analysis is to complete the short circuit analysis, which has two primary goals. One is determining the maximum short circuit current that will be seen at any given point in the system. Now, the reason for that is, well, what it takes to do that is to have an accurate voltage representation and then somewhere near an accurate impedance summation, and that's where the data collection comes in. So to determine the short circuit current, we need voltage and impedance. Now, the second function as far as the short circuit analysis is once we've determined what that worst case current is, and it will occur during the first half cycle of usually a bolted fault. The second question is, will our equipment survive and will it work properly in the system? And again, that particular feature or function is referred to as equipment duty. As equipment is designed, built, and manufactured, the manufacturer is providing technical parameters, usually in the form of a data sheet or on a nameplate of the panel or the switchgear, the rating that he's has tested or guarantees that equipment to work properly. And so consequently, that needs to be entered as we're doing the modeling in EasyPower. And once it's there, the tool will automatically verify whether or not the equipment's adequate to the task. Now, so jumping back into the tool, that's kind of how I look for that, or what we see is, for instance, this particular bus has got on its data dialog box, it's got a bus rating for basically the current carrying capacity, and then the bracing rating, which is again the maximum current that the piece of equipment is guaranteed to work within properly. So if this data is not there, we're not doing that check. Now, the reason for kind of going into this more specifically is there is a feature or a capability in EasyPower called the database browser, and that's what we would use to verify this. Now, another point I would make before I go to the database browser is that one way to deal with these, because they very well be common values as we look at our system, is to set up an EasyPower default values or default templates. So as we create a cable, it's more of a typical size and rating, as well as buses, breakers, or other devices. So let's touch on that real quickly before we go to the database browser. I'm in EasyPower, EasySolve, Database Edit. I'm going to go to the Tools Focus up here on the top tab and look at the equipment list. And as I select an element here, this is the default settings for what the tool is using. Let me just say a couple words about this. So again, this is a global setting, and these are going to be my default values as I pick up the bus icon drawing my one line. Now, if most of my buses are going to be panels, I might want to set up, let's say they're square D panels, I might want to set up my default value to be square D, and I want to have it a certain, and let's say I know they're all going to be 200 amp panels, and let's say I know from the data sheet that they're braced or set up for 42K, and they're copper material, and they're going to be freestanding or flush mounted. So if this is what a majority of my panels will be, my buses will be, by setting up this default, when I add another element now to my one line and I go in and look at the data dialog box, it'll have all those values in there. Likewise, if we change anything now, likewise if we draw a cable, if I come back here to my cable rating, and let's say in my low voltage cables, everything, most of the time, I'm going to be using a THHN, and let's say most of the construction or most of the buildings wired out with 4-aught, then I can use this as my dimension, and it's copper, and we're routing it through steel conduit by setting this up as my default. Next time I pick up the cable and put it in my one line, it'll be set up thusly as a 4-aught copper through a steel conduit. Okay, so that's the default settings, and any piece of equipment I can set up likewise. If I'm using all square D breakers, I might want to set up multi-case circuit breakers using square D. The point is, if I'm using one of these elements a lot, it's easier to set up the default settings and then just modify as we run across an element that's somewhere different. Okay, I'm going to take this off of here, go back to my home tab. Now I started to talk about the database browser, which is, once I've drawn my very simple one line from my source to my lowest load, and again, before I got to all of this drawing, I would say draw this one particular load line. I would go in and look at my database browser. If I go to File, Database, click on Database Browser, it brings up a full grouping or analysis of the one line that I've entered so far. So what you see here at the bottom, there's 36 buses or nodes that have been created as I drew this one line. And if I go up and look in the equipment summary, I can group the buses together, and this shows me again the data that's been entered for each one of these buses. And the first thing that I notice is that none of the buses have a capacity rating, and none have a bracing rating. And again, this is the data that's required for equipment duty calculations by the tool. And so rather than beat this into the ground, my point is the tool does these calculations of these, the equipment duty calculation automatically, and you're wasting value by not putting values in here for it to be able to compare. Now, we'll see a lot of other columns here, some of which don't even apply to maybe my facility. I can configure this report and reconfigure the number of columns that are showing and the like. And if you need questions on that, we can handle it in a separate conversation. All right, so likewise, if I'm looking at, so this is buses. So let's say I want to look at my, usually you want to look at transformers. And again, in this particular case, he didn't have a transformer. Cables is another one to look at. And here, it may not be possible to tell at this level if there's a problem other than recognizing commonality between, say, cables that we know are grouped together on certain voltage levels, and then whether or not they show similar values. And if they're different, it could be that we didn't use the calculate button when we entered a different length for that particular cable. Now, to that end, if that's the case, I'll come back to that in a second. All right, so that's cables. The other thing I want to look at are my low voltage breakers. And again, what I'm looking for are missing blocks of data. And frequently this will be in the manufacturer if we haven't designated a type or a manufacturer, and it looks like he has in all of these areas. The one that looks like it's a little bit awry is we don't have values here for instantaneous settings, even though he has a manufacturer. And given that, we can go in and look for it just by double clicking on that yellow column. And as we go over here and look at the phase trip, we see sure enough he hasn't set up an instantaneous trip setting. Now, I think part of, and I'll come to this in a second, his response was, well, there was a label over the dial on the breaker, so I couldn't collect that data. Well, this is another case in point. What is it that you want to do? Do you want to analyze the system, or do you want to let a label stop you from updating what's actually being done? So recommendations would either one, use a maximum setting because that's going to give you the worst case scenario, or two, and make a note to yourself or make a note to the client that I used maximum because the label was covering the dial setting, or two, rip the label off and record what you actually see on the, or at least lift it up to the point where you can see the dial setting. Again, either case, you need to make a note to yourself. Now, so that's that function. This utility is called Database Browser, and it's extremely valuable in finding missing data and kind of troubleshooting a problem. Now, we talked about the default settings. One other thing I would touch on, and that goes to my, back to my material. All right, so we talked about cable values. We talked about the database browser, and again, we're primarily looking for gross data entry errors and an indication that you're missing something, but it's not really clear whether it's a data entry problem or a problem with the data being collected. Okay, the next question that came up is how do I deal or connect panels? And in this particular case, it was just a lack of awareness or a lack of training. And so let's kind of jump into where we do that. So we have a couple cases where we've got a database, we've got a panel that was set up. Now I've deactivated this, and right at this point I'm going to activate it. And that's how you can isolate, if you've overdrawn a system, that's how you can isolate extra parts until you sort out the mechanics, is by deactivating it. And what we see is in this particular, I guess it was which one? Yeah, this one up here is the one I want to deactivate. Because I've already put the loads in. All right, so we have a panel set up, and we need to tie it into an existing panel. The way the tool works is literally just connect it to the panel, indicate where you want it coming in. Now, we've already labeled the cable. When we come into the panel, we can see that we've set this up. We've got capacity ratings on it. We've set the incoming device. But under description, we haven't told it what the panel schedule looks like. On this particular case, we know that the sub panel comes in the first three circuits 1, 3, and 5. So let's say this particular panel has 12 rows. We're looking at the left side. Here's circuit 1, and we know rather than a load or a motor that this is going to be a sub panel. So as we tab out of here, we tell it which cable leaving this panel we need to connect to, and we know it's A to B. And we also know in this case it's going to be a 3-phase cable. And so by doing this, we've created, at least let the tool know how the connections to that second downstream panel work. But also by doing this, we've illuminated the data device. So this is the circuit that's going to be feeding that particular panel. And so we set up that breaker, or the breaker that's going to be feeding that panel thusly. So let's set it up with 150 AF. And this would be exactly like we were setting up as a freestanding breaker. So now that I've got my breaker set up here, you can see that the tool pulled in the conduit and cable ratings for that downstream breaker. Now that I've done that, I can, before I close out this panel, I want to go to summary. I want to calculate downstream load. And now it pulls in the load that we have from that downstream panel. All right, so then if there's any questions on that, we can kind of handle it offline. Let me see. The handouts are on in the control box, and yeah, Saeed, yeah, good question. So the topic of single phase, in fact, I'm about to jump into that. So how do we handle arc flash calculations at this point? The fact of the matter is there's not a single phase model yet in terms of arc flash modeling. There is, and so right now what we're left with is the IEEE 1584 model, recognizing that there are certain limitations when it comes to low voltage and low energy. And that means that the tool is valid for 208 volts, but the results will be high in terms of incident energy calculations. And if you look at the verbiage in 1584, it says if you're supplied by a transformer less than 125 kVA at less than 208 volts, there's a low risk of arc flash event, or you can disregard those elements. It also talks about a 2-second rule through which you can limit the calculation time to reduce the excessively high incident energy due to long trip times. Well, before I do either one of those, I really want to know what the currents are. And to Saeed's question, EasyPower currently only models 3-phase systems. We expect to have by the end of this year a compute engine for single-phase short-circuit calculations. Until that time, again on the handout list, there is a how to handle single-phase short-circuit calculation application notes, effectively a workaround for the tools that will give you the ability to take the 3-phase results that the tool provides and then compensate that for single-phase calculations. Now, meanwhile, and in addition, we have it on good authority that there will be an updated model 1584 by the end of the year that is a little bit more specific than the vague reference we currently have for low voltage arc flash. So that even in the current standard, there is wording that says use sound engineering judgment as you're dealing with any of these adjustments or tweaks to the IEEE model. And so that's why I am offering these handouts. If you, for some reason, can't download them from this control box on the webinar, send me an email and we can get them to you. But what you're left with, I guess is the way to put it, is based on a decision with your client. If you want to have labels on single phase circuits or you want to have labels on 208 panels, then let's kind of look at what's showing up on the calculations. And to my point, so here we're going to go to short circuit focus, and I guess I didn't do this one. And what I didn't do was tell it which cable we have coming in on it. So let's try that again. Incoming 60 amp. All right, we're in short circuit focus. We're going to fault this particular bus, and we're going to look at incident energy. And what we see, and this is what you want to do in any case, is the next step is to go to arrange for arc flash, and the tool shows me what it's using for calculations. So here in this particular case, we have a voltage fault current at this particular panel of 2,755 amps. Again, this is a three-phase number, of which the maximum arcing current would be 1,700 amps. At that point, we have, and the tripping device is the B505 circuit that we set up here. So because we set up those independent settings, we're in pretty good shape. Let's go down to this one that wasn't set up. Let's see what happens here. So we're showing 10 calories on this particular device, and we see that its upstream trip device is the fuse, which is back up here by our utility icon. So clearly we haven't set up, at the very least, the main breaker, and I suspect another breaker along the way. The point I wanted to get to, though, assuming this is the way things are wired up, and I'm disregarding the main in this particular device, we see a maximum bolted fault current of 2,000 amps. Arcing current is 1,400 amps, and we have a trip time of 6 seconds. Well, all that doesn't make any sense whatsoever. And the paper that I am including as a handout is essentially reflects that anything below, at 240 volts, anything below 4,000 amps will not self-sustain for even one cycle. So let alone the 6 seconds that we're talking about here. So what are your options? And hopefully I didn't bobble that too much. What are your options as far as someone conducting this study? Well, you need to talk to your client and talk about what essentially the situation is that he needs to have a label if anything's going to be opened up and electrified above 50 volts. Since 1584 is pretty vague about arc flash at those voltages, and it says in essence you can disregard those low energy systems, one solution or one option may be just to fix the calorie label and say, okay, assume that the maximum calorie inside that panel is 1.2 calories per square centimeter, and that needs to align with the client's corporate policy and how he's going to train people to recognize that system. And again, this is based upon the current level and the time calculations that we just looked at. Now, on the other hand, we might want to go in and, so here we're talking about a fixed energy level. Another alternative is to limit the calculation time so that it produces a calculated result inside or near this appropriate level. Now, in either case, we're talking about doing something than just letting the tool, the model, calculate the results. And that's why we suggest, and IEEE reinforces, that sound engineering judgment needs to prevail. So let me just kind of show you how this works in EasyPower. In short circuit, we go to short circuit options. Here we find the arc flash hazard tab. These are the tweaks, if you will, that IEEE 1584 model allows. First of all, it's automatically comparing 100% arcing current with 85% arcing current. In this case, we're excluding the main of the panel, so that's why, whether or not it looks like we have a breaker set up, but it's being excluded, and we're relying on the fuse to trip the arc fault. And we have already reduced the maximum trip time, or the maximum calculation time, for circuits under 250 volts to 2 seconds, and we're still getting a 10-calorie result. So one option is to reduce that number based upon what the current is. And again, the Lang and Jones paper suggests that the arc will not sustain even for one cycle at these levels. So that's one possibility, reducing this number further. Secondly is, if I go back to database edit and I look at this particular panel, if I go into its arc flash tab, rather than calculate it, I can force it to a specific instant energy. And if we say 1.2 calories and put my arc flash boundary at 18 inches, I might be justified, or the client might agree, based upon what it is he's trying to do for low voltage panels. So this is where I would do it on a localized basis. Now, again, either one of those I would not do without a serious conversation with the client. All right. The point here, and this just came up last week, and someone doing something like this, and that is making the comment that no PPE is required because the bus instant energy falls below 1.2 calories. Now, I personally think this is a misreading of the fact that NFPA 70E has done away with category 0. Below 1.2 calories per square centimeter, they're not saying there's no arc flash potential. They're saying that 1.2 calories is the point at which there's a 50% chance of a second-degree burn to exposed skin. So if I have no PPE on, there is still a potential for me to receive burns. And so I would be careful using this terminology. And in my discussions with the client, I would specify that there's a certain minimum for qualified workers if we're going to be in the area, even at these designated low calorie exposures. Okay. Just because we go through this a lot, I think it's important, and this is where the training, I think, is paramount, is that just because we're in an area where there's no specified PPE required, that doesn't mean that somebody can't get hurt. And that, I think, needs to be comprehended in my training of the employees. Okay, so what we've talked about today is we want to start with a simplified model to understand the process. When possible and when it's productive, set up equipment defaults for the project to have known values entered in when we first build the one line. Utilize the database browser to locate missing data from a 5,000-foot view. use a range for arc flash to make sure we understand the available fault current and which upstream tripping device is in play for any particular bus, especially if it doesn't make sense on an initial viewing, and to utilize the arc flash hazard settings and short circuit options when to make sure that it matches what we're trying to do in our calculations. And above all, use sound engineering judgments when the results for low voltage and low current buses are unrealistically high. Thanks everyone for attending today. By all means, check out updates to the website, which we do weekly. We do now have online training that's available for purchase, and considerably same content as a live regional training session, but you don't have access to the trainer. So depending upon your needs and how quickly you need the training, you may want to check it out. Thank you for attending, and we'll talk to you in a couple weeks. Have a good day.